All right, everyone. It's 1:30. Hopefully people were able to have a good lunch and maybe also go for a walk outside. Is there anyone else waiting out there? Okay, we're good. Okay. So I'm pleased to introduce our next speaker, who is Alper Altunas. Alper is a software engineer in the ocean section, and he'll be discussing MOM6 and the Community Earth System model. So take it away.
Thanks, Dan. Yeah, so I'm a software engineer at the oceanography section here at NCAR, working primarily on MOM6 and also contributing to the Crocodile project. So in my talk, I'll try to give a quick introduction to both MOM6 and CESM, and I'll also go over a quick start guide describing how to use MOM6 within CESM. So here's my outline for my talk. I'll, again, go over CESM, the basics, and then MOM6, particularly within the CESM framework. And I'll go over a quick start guide describing first how to download CESM and then how to use CESM, creating, building, running a MOM6 experiment. So let's begin with the overview. So what CESM or Community Earth System model is our flagship model for simulating the Earth's past, present, and future climate states. It's the result of over 30 years of development. It has over 4 million lines of code, and it's a committed model. What we mean by a committed model is that it's available to the research community openly and freely. It's open to community contributions, and as NCAR, we are committed to support and maintain CESM in the long term. CESM is used for a variety of use cases, like simulating past observed events and trends, understanding climate variability, studying subseasonal to multidecadal prediction, and also providing actionable societally relevant information. So CESM is a coupled model. That means it consists of individual components coupled together. So each of these components, which are atmosphere, ocean, land ice, land, sea ice, biogeochemistry, and so on, these solve the governing equations corresponding to things like fluid dynamics, thermodynamics, biogeochemistry, and so on. And at regular intervals, components that share an interface exchange information, boundary conditions among themselves. And so here's an example of an information exchange between the atmosphere and ocean. And what's being exchanged between these two include things like wind stress, sensible heat, precipitation, evaporation, radiation, and so on. CESM architecture is based on what we call a hub and spoke architecture, where each of these components are coupled through a central CESM coupler. And so MOM6 and SICE, for instance, communicate through this central coupler. And we have three types of components: active components, data components, and stub components. Active components, like MOM6, evolve in time. They do computations and exchange information at regular intervals. Data components don't do any computations, but they provide forcing data, but they don't evolve in time. They basically read in data from data stream files and then provide it to other active components. And then there are stub components that are basically placeholders. They don't do any computations, and they basically are there as placeholders. So for each component classes, we have active, data, and stub components. For the atmosphere, the active component is the CAM atmosphere model. The ATM is the data atmosphere model, and SATM is the stub atmosphere model. In the case of ocean, we have MOM6 as our active ocean model. Data ocean and stub ocean are our data and stub models for the ocean, and so on. So the reason we have these different types of components for each component class is, so let's say when we want to only focus on ocean, study ocean, we can have an active ocean model and we can have data atmosphere, data runoff, etc. That way we have computationally less expensive model and we can actually isolate our concerns and focus on ocean with, not without adding additional, complexity into the system. So throughout this workshop, you'll hear a lot about cases. In CESM world, a case is a specific experiment, a simulation instance. And at a minimum, we define a case by three things: a case name, it's a unique identifier for a case; a comp set, it's a specific combination of those component models that I just went over; and then resolution is the collection of grids for each of those components. SEAM is a Python library that comes with CESM. It's a software infrastructure to manage CESM cases. It's the interface between you, the user, and CESM. It lets you create, configure, build, and run CESM cases. And I'll briefly go over how you can use SEAM to do those. But let's first go over those two important concepts: the component sets and resolutions. So again, a comp set or a component set is a specific combination of models. And we refer to comp sets with long names. These are long string identifiers precisely specifying what we include in our experiment. These are delimited by underscores. And here I have an example. This is a typical comp set we use in ocean modeling. So the first part of this comp set, 2000, is the initialization time. And we have these three commonly used initialization times. 1850 is the pre-industrial conditions, 2000 is the present day conditions, and HIST is the historical transient simulation. In this case, we work with present day conditions, which determines the initial conditions and forcing data. Next part of this long comp set name refers to the atmosphere configuration. As you can tell, this is DATM, or data atmosphere, and the percent notation here is used to further customize the model. In this case, we are telling CESM that we should run this DATM model with this specific JRA forcing data set. Next, we have a stub land model, and then a data ice model, again, configured to provide SSMI forcing data set. And then we have the ocean model, MOM6. So we have an active ocean model in this comp set. And in this case, we don't have a BGC configuration, but to enable BGC, all we have to do is to add this percent marble-bio right after this MOM6 specifier. Again, for the data runoff, we have JRA forcing data set specified. And the last two are stub glacier and stub wave models. So when we create a new case, in practice, what we actually do is we have these comp set aliases, like short identifiers for these commonly used comp sets. So instead of that whole long comp set name, in practice, what we would specify while creating a new case is this short name, C_JRA. And in CESM nomenclature, C comp sets are comp sets with ocean-only configurations, where ocean is the only active component. And here's the diagram showing this comp set. See, MOM6 is the only active component. So this is ocean-only case with data ice, data atmosphere, and data runoff for providing forcing data sets for MOM6. Another commonly used comp set in ocean modeling is the G comset, G_JRA, where we have both MOM6 and SICE as active components forced with data atmosphere and data runoff. SICE is our sea ice model in CASM. So if we want to simulate ocean biogeochemistry, what we can do is we can add marble to our component set, in which case we would have this G1850 marble_JRA. And another commonly used configuration is the fully coupled comp set, where all of the components are active. CAM is the atmosphere model, SICE, sea ice model, CLM, land model, MOM6 ocean model, Mozart is the river runoff model, Waywatch 3 is our windway model, and then in this case, glacier model is a data model. So when you create experiments, you specify the comp set and a resolution. A resolution is, by resolution here I mean the horizontal resolution of model grid, which determines result physics and spatial scales, and also computational cost. As you increase the resolution, the computational cost roughly increases by a factor of 8. And in workhorse global climate simulations, we typically run at 1 degree resolution for the ocean. But for regional models, we can actually increase our resolutions to say 0.1 degree or higher, which allows us to simulate, finer scale physical, processes. So in CESM, typically we run atmosphere and land on the same grid, and ocean and ice are also usually share the same grid, and other components have their own default grids, pretty much used for all comp sets. And that means the resolution identifier that we specify when we create a new case has two parts. The first part is the atmosphere land grid, F09 in this case. And then the second part is the ocean ice grid. T232 is our workhorse ocean MOM6 grid that we use for our global simulations. And there are some exceptions to this naming convention, but I'll skip that. So yeah, that was a quick overview of CESM, the CESM framework. Now I'll briefly describe MOM6, specifically MOM6 and CESM. So Alistair gave an introduction on MOM6, particularly the formulation of MOM6. Just to add a few more things, it's a consortium model. So it's primarily developed by NOAA GFDL and the consortium members, including us, NSF NCAR, NASA, Navy, universities, and international partners. As Alistair mentioned, it solves hydrostatic Wisniewski or non-Wisniewski equations. It uses the ALE vertical coordinate algorithm. Again, we'll have a talk on that, but just to say a couple of things, it minimizes spurial diapicnal mixing, and it enables physically realistic water mass evolutions, which allows us to simulate sea level rise or wetting and drying. So it supports a variety of vertical coordinates. Again, we will cover those in the following talks. And in CSM3, the upcoming major CESM release, MOM6 is the primary ocean component, replacing the old POP2 model. Just like a CESM, MOM6 has a variety of applications like global climate and Earth system modeling. It's used for forecasting, hurricane and seasonal forecasts. It's used for idealized studies, and it's also used for regional ocean modeling. So both CESM and MOM6 are maintained and distributed on GitHub as separate repositories. This diagram summarizes the repository structure. Each box is a GitHub repository. So we have this CESM repository that has all of its components as submodules. So it encapsulates all the components and libraries as Git submodules. In the case of MOM6, there's this interface layer between CESM repository and MOM6 repository. And so in this MOM interface repository, we have CESM specific applications and tools that basically facilitate incorporation of MOM6 into CESM. So in this gray box here, I show the main MOM6 repository. This is under MOM Ocean GitHub organization. This is the central MOM6 consortium repository where everyone, each member synchronizes. So when we have made changes in NCAR MOM6, we submit a pull request to MOM Ocean, just like all other consortium members, and then we periodically receive changes from this repository to stay in sync with the remaining members of the consortium. Again, Alistair went through these governing equations. Simply, these describe things like conservation of mass, conservation of momentum, thermodynamics, equation of state, etc. We discretize these using finite volume approximations. We add in computational routines and parameterizations to account for small scale processes that we cannot resolve with the grid resolutions that we have, and end up with over 100,000 lines of Fortran code that we call MOM6. So for horizontal grids, MOM6 horizontal grids, there are a few options that we can work with. Cartesian grids are usually for idealized applications. Spherical grids are used for both global and regional domains. And in the case of spherical grids, we have the option to work with rectilinear grids or curvilinear grids. Curvilinear grids are more commonly used. And when working with curvilinear grids, it's important to keep in mind that there's a distinction between the index space and the geographic space. The logical index space is always rectangular and uniform, whereas the spherical grid or mapping of that logical index space onto real world leads to non-uniform or curved line like you see here in this right panel. So again, MOM6 uses the Arakawa C grid horizontal staggering. We have the scalars in the cell centers, like temperature, salinity, tracers, and so on. Velocities are at edge centers, U and V points, and vorticities are at the corner points. So MOM6 has these two different memory modes. This is a bit technical, but the reason I'm including this slide in this talk is because when we're working with regional domains, we need to work with this symmetric mode. And the distinction between non-symmetric and symmetric mode is that in the case of non-symmetric mode, we have arrays that have the same shape for all the staggerings, whether the quantity is at the cell center or edge centers or corners, they will all have the same shape. But in this case of symmetric mode, the array shapes depend on the staggering location. And again, for regional models, we will work with the symmetric mode. Again, so here's the list of various vertical grids supported by MOM6. We will, again, cover all of these in the following talks. But what I'll say here is that for regional domains, we will work with the Z-star grids. These are geopotential grids where we define layer thicknesses based on the depth within the water column. So I'll quickly go over MOM6 input and output files. The first input file set is runtime parameter files. These are text-based files. Then we have input data files. These are netcdf files, things like the grid files, initial condition files, forcing files, and so on. And we have a set of output files, like the log files, again, text-based log files. And we have history files that contain average or instantaneous model output requested by the user. Restart files are used to continue a simulation from where it left off. So here are those 4 commonly encountered MOM6 runtime parameter files. Input nameless is for general model configuration. We rarely touch this input file. What we generally work with are the other three files: mom input, mom override, and diag table. Mom input file is the main mom6 runtime parameter file where we can specify internal model physics parameterizations, and some computational behavior is defined in mom input. And we can override what we specify in mom input through an optional file called mom override. And the diag table file is again a text-based file where we specify the history output that we want the model to produce. These will be netcdf output files, including diagnostic fields, either instantaneous or averages, either the entire domain or certain sections can be requested through this diag table input file. In CESM, actually all four of these files are automatically generated for standard configurations based on the comp set and grid that you specify. And there are CESM mechanisms to modify these files, as I'll describe in the next section. But the general syntax of runtime mom6 parameter files is quite simple. We have these key value pairs. Key is the parameter name, value is the value that you want to set for that particular parameter. As for the input data files, again, these are binary netcdf files. We commonly have this list of input files. The supergrid file is the file where we define the horizontal grid. The resolution or the grid metrics are defined in the supergrid file. We have the topography file defining the ocean bathymetry. We have the vertical grid file defining the vertical grid, like Z levels or layer thicknesses. The initial conditions file will include things like the initial temperature, salinity, velocity, fields, and so on. And we can have other input files like geothermal forcing, tidal forcing, depending on the configuration that we have. These files are also automatically staged in your run directory in CESM for standard configurations. So for the output files, we have a number of log files. I'm listing some of them here. The mom parameter.all file lists all of the mom6 runtime parameters used for that particular experiment. Mom parameter.short is similar, but it only shows the parameters whose values differ from default values. Available diags file is quite useful. It lists all of the available diagnostics fields that you can request for that current configuration. Ocean stats file has various model statistics like CFL number, mean sea level, and so on. History files, these are netcdf files, have average or instantaneous model output that you request through the diag table file. And these may include 2D surface fields like sea surface height, sea surface temperature, and 3D fields as well. Restart files are again used to continue a simulation from where it left off, and the frequency of restart files can be specified in runtime parameter files. Okay, so that was, again, a quick overview of mom6 in CESM. Now I'm moving on to a quick start guide, and I'll describe how to use or how to create experiments in CESM for mom6. But before I begin, I should mention that I will walk through how to download CESM, how to create, build, run, and customize a mom6 experiment, which may be a lot to cover in a short time. So don't worry if you're not following everything. If everything doesn't make sense right away, we'll have subsequent talks with more details on various aspects, and I'll point you to documentation and other tutorials, and we'll also have dedicated hands-on sessions. But the goal for this talk is really to give you a big picture understanding of the workflow and overview, and get you familiar with some of the high-level concepts that matter when working with CESM. So as I mentioned, CSM is distributed via GitHub, via publicly available repository. And downloading CSM has 3 steps. First, you locally clone CSM repository. And initially, that local clone will only have utilities that will help you fully download CSM. In the next step, you choose a specific CSM version, and then you run a tool called Git Fleximod. This is an in-house package manager for CSM that allows you to pull in all of the component repositories, mom6, cam, size, and so on. So initially, when you clone CSM, it'll look like this. It'll have these utilities. And when you run that Git Fleximod tool, you will obtain all of the components and libraries. So this is the command that you run to clone CSM, git clone, and the CSM repository URL. Then you cd change directory to that local CSM directory, and then you can check out a specific Git version or CSM version, and then you run bin git flexmod update command. This is the step where all of your components are downloaded locally, and it takes about 5 minutes. So in that previous slide, I described how to download the standard CSM distribution, but in this workshop, we will work with a custom version of CSM. It's a Crocodile fork, and all of the changes in that fork will eventually make it to standard CSM, but for regional modeling purposes, we will work with this specific fork. And the overall workflow is pretty much the same. You again run git clone, but instead of the ESComp organization, you will have this Crocodile CSM organization. And you will check out this specific workshop branch, workshop_2025, is that correct? And then we will run this git flexmod update command. So before working with CSM, after downloading it, you need to make sure that CSM is ported to your machine. On supported machines like Dracho, that's already done. You don't need to do anything else. But on other systems like local clusters, you will have to port CSM, and there are some steps like installing software dependencies, compilers, MPI, netcdf, ESMF, and so on. And you also need to modify some configuration files in CSM to add and adapt entries. And there are documentations on how to achieve that. But assuming you've downloaded CSM and made sure that it's ported to the machine you're working, you can quickly create a new case using this create new case tool that comes with CSM. It's under seam scripts subdirectory. And at a minimum, this create new case command expects 3 arguments: the comp set argument, the resolution argument, and then the case name. The comp set in this case is GJRA, and recall it's the comp set where we have ocean and ice as active components. And the resolution in this case is TL319_T232. That's our workhorse resolution for MOM6. And here I happen to name this case my ocean ice case. It could be any identifier. But this -- case argument also determines where your case is created. So in this case, I will create this case in my current working directory under my ocean ice case subdirectory. And after you create your case, you will run case.setup and case.build commands. When you run case.setup, C generates some input files needed for building the case and also running the case. When you run case.build, C compiles a specific CSM executable specific to that case that you're working on. And after the case is built, you can submit the case, and that'll push that job into the job queue. And as a reminder, on HPC systems, a job is a unit of work you submit to run, and a job queue is a list of jobs waiting to be executed as resources become available. And a project is basically an account shared by a group of users sharing a common allocation, like compute hours. So when you execute case.submit, that command submits a CSM execution job to the job queue. And the job will then start running the CSM executable as the resources become available. And you can monitor your run progress by checking this log file called case status. It's a text-based log file that has, the latest status of your case. In this case, right after submitting the case, it'll have these messages: case submit starting, case submit success. And after case start running, this log file indicate that. And eventually, when the case is successfully completed, again, you'll be able to find that out through this case status file. Alternatively, you can use this qstat command on Dratro to check your job status. And after a successful run, what will happen is, by default, CSM will move all of your output files to another directory called the short-term archive directory. This happens automatically. And you can find the location of this directory by running this cool tool called XML query. So the XML variable corresponding to the short-term archive directory is called dout_s_root. So if you do XML query dout_s_root, SIEM will return that location where all the history, restart, and log files are moved to. Or alternatively, you can actually disable this behavior by setting dout_s variable to false, but this has to happen before you submit the run. So there are three important case directories regarding a CSM case. One is the case root directory. This is your control desk for a case instance. This is where you customize your case, where you build, set up, and submit your case. It has these XML files, including information on your case configuration file, the case configuration. You have these tools that I just went over: case setup, case build, case submit, and there are some mechanisms to customize your experiment through this directory, case root directory. The other important directory for a case is the run directory. This is a temporary directory that's typically placed under a scratch space. A scratch space is a temporary storage area on HPC system like the Dratro. So the run directory will be under scratch directory, and the input files will automatically be staged in that run directory. But one thing to note here is that you should not modify input files in the run directory, because those are automatically generated and your changes will be overwritten. So any changes to the case configuration should be made in the case root, not in the run directory. The third and last important case directory is this short-term archive directory. Again, that's also under the scratch space. And here are those three case directories. First, you have this case root, XML files, tools, and mechanisms for making changes in the case configuration. Then you have your run directory, initially empty. You'll have your archive directory, again, initially empty. So when you execute case.build and case.submit, all of these input files will be automatically created under the run directory. And while the case is running, all the log files, history files, restart files will be saved under the run directory. When run is complete, the short-term archiver will automatically copy or move all of your log files, restart files, and ocean files under your archive directory. The only file that remains under the run directory is the latest restart files, which is handy if you want to extend your simulation beyond what it initially ran. So I'll also talk briefly about how to customize cases in CESM. There are three mechanisms. The first mechanism is the XML change mechanism, which I briefly mentioned. And it's quite easy to make changes in your cases using this mechanism. All you have to do is to run XML change, and then you specify your variable name, enter new value. And through this mechanism, you can make changes in general settings like the run length, restart frequency, coupling interval, and so on. You can also make some high-level component-specific settings like number of tasks, memory mode in the case of MOM6, and so on. And again, this example shows how to make changes through this mechanism. User NL mom or any user nameless file under your case root allows you to make changes in your internal model parameters. In the case of MOM6, we can change things like mixing coefficients, time steps, internal time steps, or physics and parameterizations are all controlled through this user NL mom file. An example of a change is here where I set the thermodynamic time step to 1200. Source mod is another mechanism to make changes where you place your modified source code or input files under this source mod subdirectory within your case root. And this mechanism is for changing MOM6 input files that cannot be changed via the user NL mom file. Examples are diag table and input nameless file. So here are some more examples of XML changes. By the way, XML variables are some high-level variables that determine the configuration of your case. So for instance, in this case, I change with these two XML change commands, I change the duration of this simulation to 3 months. And I can also control the job walk clock time. I set it to 1 hour. And after running an initial simulation, what I can do is I can set this continue run to true to instruct CESM to continue the same run from where it left off. Or I can change the debug mode. I can set debug equals true, and that'll turn on compiler debug in case you run into issues and would like to diagnose what's going wrong. There are some MOM6 specific changes as well that can be applied through XML change, like you can change the number of tasks, you can change the coupling frequency, and you can change the memory mode. One thing to note here is that certain XML changes will necessitate rerunning case.setup or case.build commands, but SIEM will not notify you when that's the case. So one thing that complements XML change tool is XML query, where you can use to get the values of XML variables. Like in this case, I run XML query render, and that'll return the run directory for this particular case. Another useful feature of this tool is that you can do -p and then a substring like MOM6, and the tool will then return all of the XML variables, including MOM6, in its name. Or you can specify this -- description flag that'll return a description of a particular XML variable. Or -- valid -values flag returns the valid values for a particular XML variable. The second mechanism, again, is user NL or user nameless mechanism, where you can modify internal model runtime parameters. It has the same syntax as mum override, so it's key value pairs. Here I have 3 examples of parameter changes. I set the parapletic time step to 900. I changed the background horizontal thickness diffusivity. And in this third case, I changed the interpolation type for determining boundary layer depth. And notice here that I have this % sign. That means that this particular interp type is a module parameter that belongs to the KPP module. So in summary, as you can tell, CSM is quite flexible and customizable, which can feel like a lot at first, but for standard experiments, working with CSM is actually quite straightforward. All you have to do is to run this create new case command, and then you run case.setup, case.build, case.submit, and that's it. That's how you run a CSM experiment. Some final remarks. So again, CSM is a sophisticated model with many components and capabilities. And I just quickly went over some high-level concepts, some high-level workflows. We will have hands-on sessions with practical exercises. And at any time, for more information, please refer to these resources like CSM tutorial, MOM6 documentation, and CSM forum is particularly useful if you have questions about working with CSM. I think I have a couple of minutes for a quick ad. There's also another upcoming event called Rigor and Reasoning in Resource Software. This is a tutorial in conjunction with the workshop on correctness and reproducibility. This will happen early next month here in this room at NSF NCAR Mesa Laboratory. It'll be hybrid, and briefly, the goal here is to reason about scientific code the same way we reason about science. We'll explore how to build reliable software through design, systematic testing, and reasoning. We'll go through some techniques like unit testing, property-based testing, where we will automatically explore edge cases, or we'll also go through automated reasoning, where we will prove properties like the monotonicity constraint that Alistair mentioned in the morning. But beyond these techniques, the goal is to share a new mindset about thinking about abstractions, properties, and hypothesize about them and attempt to refute them, just like the scientific method, and incrementally refine our understanding in code. We'll also have a session on verifiable and explainable AI. If those topics are of interest, consider registering. Here's our webpage. With that, I will stop.
Great, thanks, Alper. Time for questions. John?
So let's say I want to run CSM for like a month, and then 10 days in, the model blows up and it decides to abort. Does the initial 10 days still get saved to my short-term archive, or do I only get the restart files? My rendering.
So by default, your restart frequency is set to be equal to your full run duration. So if you change your model duration to 3 months, it'll automatically change your restart generation frequency to 3 months. So if you want more frequent restart files, what you do is, if I go back to this slide, so there's another XML variable called rest_n. So just like how I changed the run duration here, you would change your restart frequency to say 5 days or more frequent to get intermediate restart files. Does that answer your question?
Is that computation very not? Or
Relatively, it's not too much unless you're saving every time step. Yeah.
okay.
Thank you. Okay, Ellen?
So earlier on in the talk, you were saying that vertical coordinates for regional, we need to stick with Z star.
Yes.
Any chance you could expand on why?
All I know is that we are limited to Z star, but is there anyone in the room that know more?
Andrew will touch on this in his discussion of vertical coordinates tomorrow.
Thanks.
Currently not implemented, or it's not possible to go, I don't know, to hybrid coordinates in regional.
I believe it is implemented, and there are problems with, or we don't know yet how to handle the open boundary condition. Anthony,
You mentioned wetting and drying. Is that like a capability in the regional configuration of MOM6 as well?
Yes. But as far as I know, it's not very well examined, tested, so yeah. They get the grades off.
I was also curious about what are like the scientific implications of having wetting and drying? That sounds like new, like.
Yeah, well, one application I think Gustavo worked on is this ice sheet calving, where it's useful, right? When you have evolving ice sheet coverage.
Is there somewhere where we can see the full list of XML variables that we can, like all those knobs we can turn? Is that list somewhere that we can query?
Run XML query dash list dash all.
That sounds dangerous. Nice.
So in the horizontal grading, you said there are we have to specify particular cases like T 232 or something. I don't remember
Yeah.
exactly. So can a user specify the grid spacing that he requires particularly?
So what I covered here is mostly on standard configurations, but in the next talk, Manish will talk about how to create custom grids where you specify grid spacing. So that will give you more flexibility in terms of creating a new grid, new resolution.
Like regarding the restart thing, like you can change it in XML, but you can also change it in MOM input. And so do we have to account for those redundancies, or is it that if we change one from XML, it's like?
Yeah, so I realize now that I caused confusion, but in CSM, the only way you can change the restart frequency is through XML variables, but in MOM6, outside CSM, that's controlled through the input nameless file. But in CSM, you only do it through XML change.
Okay.
Since CSM supports a number of models, does it support all the nature of the grids that those models also support? And how do they exchange files? Do they interpolate on a specific grid when exchanging the file?
So I go back to diagram. So what happens is at specified interval, say MOM6 exports its export fields. And now the CSM coupler receives those fields and it maps those fields from the MOM6 grid to the destination grid, either the atmosphere grid or sea ice or whatever. So that remapping happens in the CSM coupler automatically.
And does CSM support all the individual grids that those modules or models that they can be run on?
Right. Like you mean regional, global?
Regional cases.
So some of the components like CAM, I think, don't support regional configurations, but for those like MOM6, where we can have regional domains, yes, CSM supports those kind of domains, like regional and global.
And for the setup and the build, so the setup is just setting up the subroutines for each of the component, and the build is built in the general model.
Are you referring to this case that setup tool?
You're just trying to see the difference between the setup and the build.
Got it. So case that setup is this quick step in the case configuration where C creates these extra input files like XML files and other runtime parameter files that is then used during the case.build stage and case.run stage. So, but in the case.build stage, what happens is based on those input files generated with the case.setup step, it compiles the CSM executable. So case.setup usually takes like a couple of seconds, but case.build takes 5 to 10 minutes, depending on how many models you have.
Another point to that question is, so CESM, the models can live on their own native grids. And then the coupling can interpolate, can feed fluxes, and then return those fluxes to the respective components. I don't know if that was one of the things you were asking.
Yeah, exactly. Because I know that we've actually support a number of grids, like either structure or unstructured or coordinated grids. So I'm trying to see if like those grids are also supported within the CSM framework, or it's just like specific grids within each of the model that are supported within CSM.
Yeah, I don't know, Alper, like, are there categories of grids that CESM does not explicitly support?
One thing I know is that CSM does not support Cartesian grids like that, because the CSM, ESMF mesh files need to have the coordinates in degrees, not in meters or kilometers. So that's one limitation that I can think of.
Any other questions? All right, well, we have another, I think, round of snacks out there.